Okay, part 2, preparing to contribute. Okay, so if you go to GitHub site, this is JCSDA UFO, you'll see up in the upper right, there's this fork button. So if you don't have access to our internal repositories, we recommend that you work from a fork. So it's easiest for you and easiest for us if you fork the public repository. This was back in the first release, so there's only 2 forks. There's a lot more forks of this now. But yeah, so you can fork, or maybe an institution can if multiple people at your institution work on JEDI, then you may have an institutional fork. But that's one way you can work with the repositories, so you can have your own version of the repository and to work with, and then from this version you can make pull requests to the we'll call it upstream. So how you would do this is you would first fork the repository, and then you do a git clone of your fork, which is in your account or your institutional account, and then you can add an upstream of the public. So this git remote add upstream tells Git that this is a fork of the, and this is the parent repository. So then you can do a git fetch, and this -- tag gets all the release tags, and this you can do a git fetch of all the information from upstream, and then you can do a git checkout -- track upstream develop. And what this does is it means the develop branch on your local machine, whether it be your workstation or your HPC system, it tracks what's going on the upstream. It tracks what's going on JCSDA develop. So then, as I said, before you do any kind of pull request on GitHub, you would to create a feature branch. So you can use the git flow application, but this is a way to do it just with generic git. You can do a git checkout -b, that means create a new branch, and you can do a feature my branch, and it should branch off of develop. So this is a way to do it without that git flow. And then, so after you execute this command, your feature branch is identical to the upstream develop, and then you can make your changes and merge and develop. You can periodically check out develop, do a git pull to get the latest changes, and then check out your branch again and merge and develop to keep it up to date, as was shown on previous slides. So when you so this shown on this slide too. So when you make changes, you do a git add, and then you can do a git status to make sure that, and we'll do that in the practical this afternoon. So you add the files, and to stage them, this stages them for commit. Then you can look at what files are being staged for commit, and then you can go ahead and commit. And this origin is set up to be your fork. So this git push origin set upstream, this transfers the code, your feature branch, from your local computer to your fork on GitHub. And so then you continue to make changes, and every day or two at least, you would want to check out develop. You get a pull upstream develop that gets the latest changes. Then you would check out your branch, and you would merge develop in. So this is the way to keep it up to date. And then adding tests and documentation, but be sure to add tests that execute the code. As Mariam said, we have this thing called code coverage that will check that, and it checks both of that the overall code coverage, for example, the code coverage will check that our threshold is set to about 90%. So it checks that about 90% of the lines in the code in each repository are executed by the tests. So that's what we mean by code coverage. So it checks the overall repository, but it also checks the difference. So if you added 100 lines and none of those lines are executed by the tests, then your code will fail the continuous integration testing, and it will not be merged. So if you add any code, make sure that it's being tested, it's being called by one of the tests. And also add documentation explaining the purpose of the code, what it does, how to use it, when to use it, scientific mathematical background, and known limitations or bugs. So there are two ways to add documentation. Inside the code itself is this thing called Doxygen. Both of these are Python tools. So Doxygen within the code itself, embedded within the code, are low levels, descriptions of functions, classes, and then we have on JEDI docs, which you've seen this week, we have our higher level documentation. And this higher level documentation is a repository like any other one. So it's a public, and it's on our public JCSDA page, and you can go to it in GitHub. And and you can do feature branches and pull requests on the documentation as well. So this is you can contribute to the documentation too, and you should if you're adding anything significant to the code. So this is what Doxygen looks like within Fortran. It starts with a certain bang arrow sign here, and then a code block with 2 exclamation points, and then it has these directives like a brief description here. There are details here. The syntax is like Markdown, so the double asterisk is bold, and it has lists like Markdown. You can put in a date. You can put in, there are other directives like warnings. And then in Fortran, it's nice that you right on the line for if you have some function with arguments, you can put in this bang less than sign or greater than sign, I guess. This is the description of the input parameters. And before I go to the next slide, Doxygen has it's not perfect. It has some problems with object-oriented Fortran. If you're looking at like derived types and sub type hierarchies in Fortran, it doesn't always track that correctly, and it can't follow the Fortran C++ bindings completely. So it's not perfect, but it's very useful. So anyway, so what this code this is that same example, what it looks like in C++, and sometimes it accepts several different formats. So one format is this / bang, and this is a Doxygen block. And then asterisk to define the block, and then ended by this. Oops. So you might see also in other portions of the code a triple slash, three slashes for a Doxygen block, and that works as well in C++. So there are many useful commands. So there's we showed brief and details. Oh, I should say that the equivalent of this in Fortran would be this param directive. So you can say a parameter has whether it has an intent in or an intent out. You can explicitly put in these directives in the C++. And so you can put in author, date. These are some of the directives. You can put in formulae. So this is, it accepts a LaTeX type formula style. So this is an inline formula as you would do in LaTeX. And this is a formula block. So that can be useful. And then, yeah, you can look at the documentation in Doxygen, and it has, so this is what that previous example, or no, this is I'll show the source code of this in the next slide, I think. But this is an example. This is not a real function in the documentation, but I just put it in to show you how the LaTeX integration works. So if you look at this, this is what's produced. This is what the source code looks like. So this is You can do boldfaces, you can do lists, and this is what that equation looked like. And there are some examples in the slides, but I was going to show what this looks like. It's more useful, I think, if I actually show an interactive demonstration of what this looks like. So if you go to the JEDI documentation, the main JEDI documentation page, inside JEDI and then JEDI components, it has these generic components that are components of pretty much all bundles: OOPS, Sabre, Yoda, UFO. And if you go into one of these, there's this link here for the Doxygen documentation. We publish these. You can generate it yourself too, but we publish it for the releases. So this takes you to the Yoda documentation, and there are, and you can explore this yourself. But you can go, for example, to a class hierarchy. This has all the different classes that are defined in Yoda. You can go to a graphical class hierarchy. So this has a list of classes, and coming down here, it shows class inheritance diagrams. So for example, these are all subclasses of the Yoda accumulator class. So you can come down, and the boxes are clickable. So let's go down. Let's see. Let's go down to this. So let's go to the Yoda group, which is a useful one that many people will use. So you can click on the boxes, you can go to Yoda group. This is an inheritance diagram. So what this says is group is a subclass of group base, and obs group is a subclass of group. So, and then this is a collaboration diagram. A collaboration diagram is a little different from an inheritance diagram. So this shows, again, so the dark shading here means that this is the documentation we're looking at. We're looking at the documentation for Yoda group, and Yoda group is a subclass of base. And these dashed lines here indicate that base uses these classes. So this is more of a this is an inheritance type thing, and this is a composition or a use of. This class uses these other classes, and these are the objects in these classes that this thing uses. So that's the difference between a collaboration diagram, and you can see here the public. So it has these public member functions, but it has additional member functions that are inherited from group base, that are these, and it has other member functions. Let's go to public functions, public member functions. So so it has members called like list and groups and list objects. These are all inherited from the Yoda detail group base. So you can, again, click on individual things here, and that takes you to this. And then you can click on this, and it shows you where the actual code is that defines this. So you can see where the class is defined. So that's a bit on what. And we could also go to, if we back up, we can go to, for example, individual functions. Let me. Here's a collar graph. So this shows that this create function is, well, let's go down to one more, a little more complicated. So this is Yoda detail group base exists. So this is called by all these things. Let me go pick out another example. Let's go back to group, or actually obs group. So this is, again, this shows the inheritance diagram. Obs group is a subclass of this, which is a subclass of that, and it's the collaboration diagram. It inherits things from these two, and then it uses these two. But if we go down, for example, to the generate, this shows that, for example, the collar graph for a function. So the obs space constructor calls a function, a method called create obs group from obs frame, which in turn calls this function. And then, so the things that call this generate method, these are all the things which are called by this. So so it can be useful. So that's what that gives you a feel for what Doxygen can do. And sometimes you find things that end in an _C. So this is what I was talking about, that Doxygen doesn't always follow the C++ Fortran bindings. So if you follow this call diagram back and it ends in something _C, this is a Fortran function. Then look for a routine of the same name with an _F90. That would be a C++ function that is bound to this function. And then you can continue following the call diagram. And okay, so in Doxygen and JEDI, how you would, again, as I said, as shown here, we publish the release ones in HTML, so you don't have to generate them yourself, but you can. And so you would enable OOPS, and there are similar ones for Yoda and Saber and FE3 JEDI. You use a option in EC build to generate the Doxygen. And you also have to generate these diagrams, you also have to have the GraphViz package installed. And then in terms of the developer manual, as I showed you, this is just the general JEDI documentation, and it has both usage information and some further details, like some of the mathematical basis behind the bump package, which you heard about yesterday. And as I said, this is a GitHub repository, so you can do, if you add some new feature, you can write the documentation for it and do a pull request on that, just like you do a pull request on anything else. So what it actually looks like, the documentation is written in what are called restructured text files. So this is what it actually looks like in practice, but it's converted to HTML by this thing called Sphinx, which is a Python document generator. So this converts the RST files to HTML files, which we then publish, and they're published automatically by Read the Docs. Okay, so the part 3, actually contributing code. So I'll talk about how you would actually, sort of the logistics of doing a pull request. So the idea of the terminology, by the way, the pull request is, let's say I have some code that I want to contribute to JEDI. So I'm requesting that the JEDI project pull in my changes. So that's what kind of pull request means. So if I'm doing a pull request, first of all, I don't have this circled, but this is from my forked repository. So this is JCSDA Academy. In practice, this is an old thing, but in practice, this would be JCSDA/UFO. So you would fork from the public repository. So if you're doing a pull request, first of all, you select the branch that you want to contribute to the project. And then there's this in GitHub so you would do this from the GitHub console, not from your command line. So there's a button called pull request. There's this other button called compare. This is usually before you actually issue the pull request. You can hit the compare button and see, just make sure the changes that you think you're suggesting are the changes that you want. And then it opens up a new window with details on the pull request. So the main thing here is to make sure that your source and destination branches are correct. So here, the head repository is my fork and my feature branch, and the destination where I want to pull it in is JCSDA UFO develop branch. So and you can, to see different forks, it's to include the upstream in this bar. There's this link here to compare across forks. So you can hit this button and then you can be able to see both the upstream and the local fork. And then you add oh yeah, and you make sure that there's a green light here. So you want to make sure that there are no conflicts with your branch with develop. And then, so this is what the pull request form looks like. You add a title, a descriptive title, and then there's this description block. And this is a template. So you fill in, so there's instructions here to fill in, to delete this text. You don't delete the headers, but you delete the text in here and you fill in with your own description. And a definition of done is very important. So what does it mean for this issue or this feature to be done? What is this code change supposed to do? How do we know that it works? And if there's an issue in ZenHub or on the JEDI forums where this has been discussed, maybe you've spoken with somebody that there's a bug in the code and this will fix it, then reference that discussion. And then there you select reviewers. It's often people from it's often people from the JEDI core team. If you don't know who is the proper person to review it, then we can assign reviewers. But it's always a good idea to specify someone you think might be a good person to look at the code, and then you'd go ahead and create the pull request. So again, some ideas behind the pull request: make feature branches short and focused, fill in the requested information, explain what was done and why, what does it mean for this modification to be finished? That's an important one. What's it supposed to do? And why was this done? Refer to relevant conversations, identify appropriate reviewers, make sure the code is tested and it passes all tests, because it will be, as Miriam described, it will go through automated testing, and if it doesn't pass, then it won't be merged in. And make sure it's documented. Be willing to change your code in response to reviews, and read the working principles and best practices for developers sections of the JEDI documentation. I'll get back to that. And then, so after you issue a pull request, then others will review it. So the purpose of a code review is to ensure that the overall health of the code improves over time. And what does the health of the code mean? That means the scope of the code, functionality, the clarity, the efficiency, reliability. So that's the purpose of a code review. And to be useful, they must be timely. So it's great if within 1 or 2 days, if you're being asked to review a code, if you wait for a week or two, then chances are somebody else will review it and it'll be merged before you ever look at it. So if you're asked to, we take the code reviews very seriously, and take a look as soon as you can. Courteous, it doesn't help anybody if you're being rude or saying this is not the way to do things. So be informative and constructive and reasonable. You know, the code can't be perfect, but is it better than it was before in terms of this overall health of the code? And is it moving in the right direction? And so that's what reasonable means. And additional benefits is, if you're asked to do a review, especially for new users, don't be intimidated by it. If you say, oh, I can't review this because I don't know the code, but this is a good way to get to know the code. So if you're asked to you might look. So if the pull request says this is what it does, this is the function, and then you can look at the code and say, oh, that's a good idea. That's how to make this. That's how to implement this function. And you very often learn things, almost always, and still, after years of working with JEDI, there's still a lot that I learned from code reviews. So it's a great way to learn the code. And consistent style and coding norms. You've seen the C++ coding norms test, but we don't have yet an automated testing for Fortran. But so the code reviews can help impose a consistent style in Fortran as well. So questions to ask yourself as a reviewer: does this improve the overall health of the code as defined on the previous slide? Is it clear from the title and description what is being done and why? And does it achieve what it says it does? Can the desired goal be achieved in a different way that's more readable or more efficient or more generic? So that's why it's important to say what you want to do, because there might be a better way to do it, and one of the reviewers might know a better way. Is there extraneous code that should be removed? Like, did you leave in print statements, or did the author leave in debug or print statements, or are there include statements that don't need to be there? Is the new code adequately tested? Again, this is automated, so the reviewer will know right away if it doesn't pass tests. And is the code documented? Does it belong in the code base, or does it belong in the stack? So that's another question you can look at. And then have you read these sections and where they are? If you go to Working Principles is on the top level of the JEDI documentation, and it has stuff about just general practices about what it means to review a code and tips on how to do it well. And then there's also this other, in the inside JEDI section of the documentation, there's also this section called Best Practices for Developers, and that's more details on, and there's information here on this Git flow paradigm, and a lot of what I said here is also in that documentation. And that's it. So the summary is if you're making public contributions, you work from forks, follow the Git flow principles, make sure any code you contribute is tested and documented, submit code through pull requests on GitHub, and realize that each PR will be subject to code reviews and testing. So we'll make sure it passes all the tests and make sure that the new features are tested. And realize that when you become a JEDI contributor and developer, that you may be asked to do code reviews as well.